Hello everyone, I'm Himanshu Vasnani from Department of Mechanical Engineering. I'm here with you to discuss on the subject non-destructive evaluation and testing. The subject code is ME419, unit number 3, lecture number 18, and today's topics are Snell's law, mode conversion, wave interaction or interference in ultrasonic testing. So, the today's learning objective are to provide the students with a basic understanding of Snell's law, mode conversion, wave interaction or interference in ultrasonic testing. To know about various variables affecting wave interaction or interference in ultrasonic testing. Learning outcome will be students will have an understanding of Snell's law, mode conversion, wave interaction or interference in ultrasonic testing. And students will understand various variables affecting wave interaction or interference in ultrasonic testing. So, let's start with diffraction and Snell's law. See, in ultrasonic testing, we have studied about various terms like sensitivity, diffraction, deflection, attenuation in our previous lectures. Okay, so now we are studying about refraction and Snell's law, which is a very important law when we talk about ultrasonic testing. Okay, so let's start with this. So diffraction and Snell's law. When an ultrasonic waves passes through an interference between two materials at an oblique angle, okay, and the materials have different indices of refraction, okay. Now there are two materials, okay, and the materials have different indices of refraction. Both reflected and refracted waves are produced. In this case, both reflected and refracted waves are produced. So this also occurs with light, which is why objects seen across an interface appears to be shifted relative to where they really are. For example, if you look straight down to an object at the bottom of a glass of water, it looks closely than it really is. You will find that it is really closer, but if you look at the height of the glass, and you find that there is certain height, but the angle is such like that it looks closer than really it is. Okay, so refraction takes place at an interference of two materials due to the uh, difference in acoustic velocities between the two materials. Okay, now refraction, why it happens? Because due to the difference in the acoustic velocities between two materials. You can see the figure on the right hand side, which shows the case where plane sound waves traveling in one material. Now it is traveling in one material, enters a second material that has higher acoustic velocity. So when this wave encounters the interface between these two materials, these two waves, this is encountering interface between these two materials, the portion of the wave in the second material is moving faster than the portion of the wave that is still in the first material. I repeat, see what happens that there are two materials. Okay. So when you can say the sound waves that are traveling in one material, है ना, and the enters the another material, the second material that has higher acoustic velocities. Okay, the second material has the higher acoustic velocity. Now, when the wave encounters this interference between the two different materials, okay, the wave portion which is in the second material, okay, which is in the second material which has higher acoustic velocity. So the wave portion in the second material is moving faster Okay, the wave portion in the second material is moving faster than the portion of the wave that is still in the first material. So acoustic velocity is important here. So as a result, this causes the wave to bend and change its direction. And this is referred to as deflection. Okay, because in the starting only we just said that refraction takes place at an interference of two materials due to difference in acoustic velocities between two materials. And the material which is having higher acoustic velocity, in that the wave portion is moving faster. Here in this example, the second material has the higher velocity, uh, higher acoustic velocity. Okay, the second material has higher acoustic velocity. So the wave portion in this second material is moving faster than the portion of the wave that is still in the first material. So in this way, the refraction, as this due to difference in the acoustic velocities, this causes the waves to bend and change its direction. Okay, so this is a kind of a, you can say, theory that we need to understand. So Snell's law, okay, this describes the relationship between angles and the velocities of the wave. Angles and the velocities. Understand? The two words should be known to us. The Snell's law means angles and velocities of the waves. Now Snell's law equates the ratio of the material velocities to the ratio of the sines of incident and refracted angles as shown in the following equation. Now it is taking uh, the velocities as usual, but it is taking in the ratio of sines of incident and refracted angles. In the diagram on the right hand side, you can see that you have VL1, VL1 dash, we have VL2. So when we talk about VL1 and VL2, they say that it is the longitudinal wave velocities in the first and the second material. Okay, VL1 is the wave velocity in the first material, VL2 is the wave velocity in the second material. And they have angles with them, theta 1 and theta 2. That is the angle of incident wave is theta 1. You can see incident wave is theta 1 and theta 2 is the refracted wave. Okay, so you can see the theta 1 angle is seen in material 1 and theta 2 angle is seen in material 2. So VL1 is related to uh, material 1 and theta 1 also leads to material 1. And when we talk about material 2, then theta 2, that is the refracted angle, and VL2, that is the wave velocity of the in the second material. Okay, so the relation is that sine of theta 1 upon VL1 is equals to sine of theta 2 upon VL2. Okay, this relationship is called Snell's law, and Snell's law says that the ratio of material velocities, okay, is equal to the ratio of sine of incident and refracted angles. So sine of theta 1 means uh, angle of incident wave upon VL1, that is wave velocity in the first material, is equals to sine of theta 2, that is angle of refracted wave, upon VL2, that is the wave velocity in the second material, longitudinal wave velocity in the second material. So you can understand the Snell's law very effectively through this diagram and through this equation. And this equation is important from numerical point of view, okay, because it will help you to get a relationship between the angles and the velocities of the waves. Okay. Now in this diagram, there is a reflected longitudinal wave VL1 shown and VL1 dash shown is shown. So this wave is reflected at the same angle as the incident wave because the two waves are traveling in the same material and hence have the same velocity. Okay, and this reflected wave is unimportant in our explanation of Snell's law, but it should be remembered that some of the energy is reflected at the interface. Okay, they are discussing about this VL1 dash wave in this diagram. Okay, so they say that this wave is at the same angle at the as the incident wave like VL1. Okay, because the two waves are traveling in this they are these waves VL1 and VL1 dash, they are traveling in the same material 1. Okay, so they have the same velocity, and why it is there, because some of the wave energy is reflected back at interference. So this is important to show in this. Well, it the VL1 dash has no importance in the equation. Okay, but it is important to note that down. Okay, that this is there to understand. Okay, now mode conversion. Now when a sound travels in a solid material, one form of wave energy can be transformed into another form. Okay, like they give an example. When a longitudinal wave it hits an interference at an angle, so some of the energy can cause particle movement in the transverse direction to start a shear wave. Okay, so here in this case, the mode convergence occurs when a wave encounters an interference between materials of different acoustic impedances, and the incident angle is not normal to the interference. You can see in the diagram that you can say there is something a wave coming, and here it is showing the refracted longitudinal wave, and on the left of it is written converted shear wave. You can understand that kind of conversion is happening. So mode conversion it usually happens when a wave that is traveling, okay, it encounters an interference between the materials of different acoustic impedance, and the angle, the incident angle that is there is not normal to the interface. So this mode conversion occurs every time a wave encounters an interface at an angle. Okay, whenever the wave is there and in the interfacing at an angle, this mode conversion will happen. So this mode conversion occurs for both the portion of the wave that passes through the interference and the portion that reflects off the interference. Okay, so here this mode conversion is important. Okay, now it was pointed out that when some sound waves pass through an interface between materials having different acoustic velocities, refraction takes place at the interference that we just read in the past slides. So the larger the difference in acoustic velocities between two materials, the larger the difference in acoustic velocities between two materials, the more the sound is reflected. If there is differences there in acoustic velocity, the refraction between the sound will be more. So the converted shear wave is not refracted as much as the longitudinal wave because shear waves travel slower than longitudinal waves. Okay. So therefore the velocity difference between the incident longitudinal wave and the shear wave is not as great as it is between the incident and the reflected longitudinal waves. So also when a longitudinal wave is reflected inside the material, when a longitudinal wave, that is the wave we are taking, longitudinal wave is reflected inside the material, the reflected shear wave is reflected at a smaller angle than the reflected longitudinal wave. This is also due to the fact that the shear velocity is less than the longitudinal velocity within a given material. Okay. Now comes the formula for Snell's law. Okay, now this is a kind of an expanded version. So let's First of all, understand the terminology in this diagram. Okay, so Snell's law holds true for shear waves as well as for longitudinal waves and can be written as, we can say, we have terms like VL1 and VL2. We have terms like VS1 and VS2. We have theta 1, theta 2, and theta 3 and theta 4. Now VL1 and there is also VL1 dash is there on the right hand side. Okay. Now when we talk about VL1 and VL2, they are called as longitudinal wave velocities in the first and second material respectively. So you can see in the diagram on the right hand side, you have the material 1 and material 2 written on the above and below the line. Okay, the two materials are differentiated. Then you have VL1 with an entering arrow, then you have VL2, then you have VS1, and you have VS2. There, accordingly, you have, as you see in the VS2, you have theta 2 and theta 4 in the second material, and you have theta 1 and theta 3 in the first material. So, VL1, you can say that these are the longitudinal wave velocity in the first and second material respectively, and similarly VS1 and VS2. They are the shear wave velocities in the first and second material. Now these are called shear wave velocities. Okay. And theta 1 and theta 2, these are the angle of incident and the refracted longitudinal wave respectively. Okay, we have, I told you about this in the previous slides also, and now comes the important thing, theta 3 and theta 4. These are angles of the converted, reflected, and refracted shear waves respectively. So the link, you can say the equation will be like that, that sine of theta 1 is equals to VL1 equals to sine of, sine of theta 1 upon VL1 is equals to sine of theta 2 upon VL2 and is equals to sine of theta 3 upon VS1 is equals to sine of theta 4 upon VS2. So there is a variety of, you can say, equations that you can see in front of you, and it is saying that sine of, you can say, angle of incident wave is upon, you can say, wave velocity in the first material is equal to sine of, you can say, refracted wave, angle of refracted wave upon uh, wave velocity in the second material is equal to sine of angle of converted reflected shear wave. Okay, because now comes shear wave is equal to Vs1, that is the shear wave velocity in the first material, is equal to sine of, you can say, theta 4, that is the angle of the converted refracted shear wave upon Vs2, that is the shear wave velocity in the second material. So here the Snell's law is also holding true for shear wave as well as longitudinal waves. Okay, and this is clearly shown with the help of this equation and diagram for your clear references. Okay, now critical angles. Now, when a longitudinal wave moves from a lower to a faster material, okay, moving from a lower to a faster material at an angle, and thus the wave is refracted. Okay, there is a longitudinal wave. When a longitudinal wave moves from a slower to a faster material at an angle, and thus the wave is refracted, there is an incident angle that makes the angle of refraction of the longitudinal wave to become 90 degrees. Okay, there is an incident angle that is making the refraction angle of the longitudinal wave to become 90 degrees. This angle is known as first critical angle. This first critical angle. So this first critical angle, it can be found from Snell's law by putting in an angle of 90 degree for the angle of the refracted ray. Okay. Now, as the critical angle of incidence, much of the acoustic energy is in the form of inhomogeneous compression wave which travels along the interference and decays exponentially with depth from the interface. So this wave is sometimes referred to as creep wave. Okay, this wave is sometimes called as creep wave. Creep wave is the, you can say, a technical name given to that. So because of their inhomogeneous nature and the fact that they decay rapidly, you know, creep waves are not used as extensively as Rayleigh surface waves in NDT. NDT stands for non-destructive testing. Okay, so because of the this creep waves, because of the inhomogeneous nature and the fact that they decay rapidly, creep waves are not used as extensively as relay surface waves in NDT. So when the incident angle is greater than the first critical angle, read about first critical angle in the previous slide. Okay, so when the incident angle is greater than the first critical angle, only the mode converted shear wave propagates into the material. Okay, now here the mode is converted. For this reason, most angle beam transducers, we studied about angle beam transducers in the previous types of transducers. Like. For this reason, most angle beam transducers use a shear wave so that the signal is not complicated by having two waves present. For many cases, there is also an incident angle that makes the angle of refraction for the shear wave to become 90 degrees. There is also an incident angle that makes the angle of refraction for the shear wave to become 90 degrees. Now this angle, this is known as second critical angle. Okay, this is known as second critical angle. And at this point, all of the wave energy is reflected or refracted into the surface following shear wave or shear creep wave. Okay, all of the wave energy is deflected or reflected into the surface following shear wave or shear creep wave. So slightly beyond the second critical angle, surface or Rayleigh waves will be generated. So here the incident angle for angle beam transducers is somewhere between the first and the second critical angles, such that the shear wave, such that the shear wave at an angle, desired angle is introduced into the material being inspected. Okay, now here the importance comes. Now here what happens, this uh, the figure that is you can see on the bottom side, the figure shows the modes of the waves introduced in a steel surface as a function of incident angle. Okay, as a function of incident angle of the wave generated by the transducer. Now let us first see the diagram. It is shown that on the bottom side, it is shown on the, we can say, horizontal axis, showing that incident angle is being shown. Okay, like 0, 5, 10, 15, 20, 25, 30, 35 till 80, each having a difference of 5. And there is a little first critical angle is shown at a particular angle that is around 29 degrees. Okay, and the second critical angle is also shown at around 55 plus value. So you can see that how the is are coming, that for longitudinal it has shown this angle, and for shear also it has shown the value upstairs and how the different waves are traveling. So this figure is showing you the mode of waves, the different mode of waves introduced into a steel surface. Okay. Now the mode of waves that are introduced into a steel surface as a function of incident angle of the wave generated by these transducers. Okay. It can be seen that the incident angle for angle beam transducers ranges from 30 degree to 55 degree. Now The range you can see from the where the first critical angle is marked and where is the second critical angle is marked. You can see the range. Okay, but it is important to remember that due to the refraction, the angle of shear wave due to refraction, the angle of shear wave inside the material is completely different from that of the incident angle. That is important. Now, wave interaction or interference. See, the understanding of the interaction or interference of wave is important for understanding the performance of an ultrasonic transducer. Okay, we need to understand the uh, interaction or the interference of waves. So when sound emanates from an ultrasonic transducer, it does not originate from a single point, but instead originates from many points along the surface of the piezoelectric element. So this results in a sound field with many waves interacting or interfering with each other. Okay, so when waves interact, they superimpose on each other and amplitude of the pressure, sound or amplitude of the sound pressure at any point of interaction is the sum of amplitude of the two individual waves. It is the sum of the amplitudes of the two individual waves. So first let us consider two identical waves that originate from the same point. So when they are in phase, so that the peaks and the values of one are exactly aligned with those of the other. Okay, they combine to double the pressure of either wave acting alone. They combine to double the pressure of either wave acting alone. Okay, when they are in phase. Okay, now when they are in phase. Now when suppose they are completely out of phase. Okay, so that the peaks of one wave are exactly aligned with the values of the other wave. You can see in the diagram it is shown in phase and out of phase. So in the out of phase you can see that the peaks of one wave are exactly aligned with the values of the other wave. They combine to cancel each other. They combine to cancel each other when they are out of phase. So when the two waves are not completely in phase or out of phase, the resulting wave is the sum of the wave amplitudes for all points along the way. When the two waves are not completely in phase, or out of phase, the resulting wave is the sum of the wave amplitudes for all the points along the way. So you can see in the diagram it is also written that if the waves are in phase, then it is called as constructive interference. Okay, that is 0 degree phase difference. You can see how the waves are shown. So when there is out of phase, then there is out of phase, you can see it is called as destructive interference. That there is a 180-degree phase difference is there. Okay, and they cancel each other. They combine to cancel each other. So there is no. Okay, so in this way you can go with it. Now, when the origin of two interacting waves are not the same, it is little harder to picture the wave interaction, but the principle are the same. We have primarily looked at waves in form of a 2D plot of wave amplitude versus wave position. Okay. However, anyone that has dropped something in a pool of water can picture the waves radiating out from the source of a circular wavefront. You can see that in the diagram also. Is they say that if anybody has dropped something in a pool of water, they can picture these waves radiating out from the source. The circular waveform. Okay, circular waveform. You can see how it is shown. So if two objects are dropped a short distance apart into the pool of water, their waves will radiate out from the sources. You can see in the second diagram how from 2 points the interference of waves it takes place. Okay, first diagram is showing only From one point the wave is there, and the second diagram is showing from 2 points how the interference from 2 points how interference of waves this takes place. So at every point where the waves interact, the amplitude of the sorry the at every point where the waves interact, the amplitude of the particle displacement is the combined sum of amplitude of the particle displacement of the individual wave. Okay, of the individual wave. Then it's important. It is a combined sum of the amplitude of the particle displacement of the individual. So this is also holding its importance. Okay, the amplitude of the particle displacement is the okay particle displacement is the combined sum of the amplitude of the particle displacement of individual wave. This will come in numerical, so we have to understand. The sound waves originate from multiple points along the face of the transducer. So here you can see in the image shows that the sound field would look like if the waves originated from just 3 points. We have seen the 3 points with that red mark. Okay, 1, 2, 3. You can see the red marks. Okay, the 3 points. Of course, there are more points, 3 points along the origin of the face, but we have considered only just 3 points. Okay, so it can be seen that the waves interact near the face of the transducers, and as a result, they are extensive. There are they are extensive fluctuations, and the sound field is very uneven. So in ultrasonic testing, this is known as near field or Fresnel zone. So the sound field is more uniform away from the transducer in the far field or Fraunhofer zone. At some distance from the face of the transducer and central to the face of the transducer, uniform and intense wave field develops. So now comes the wave diffraction. Now the diffraction, you can see in the diagram also how this deflected waves look like. Okay, okay, there is a crack you can see, and how the deflected waves look like. So diffraction, okay, the crack you can see on the diagram also. No? The diffraction involves a change in the direction of the wave as they pass through an opening or around a barrier in a path. Okay, so diffraction of sound waves is commonly observed. Okay, we have also noticed sound reflecting around corners or through door openings, allowing us to hear others who are speaking to us from adjacent rooms. So, in ultrasonic testing of solids, the diffraction patterns are usually generated at an edges of sharp reflectors. Okay, diffraction patterns in when you talk about ultrasound testing of solids, the diffraction patterns are usually generated at the edges of sharp reflectors or discontinuity such as cracks. We discussed about I showed you the crack in the diagram. Okay, so here they say that in ultrasound testing of solids, the diffraction patterns. Okay, in ultrasonic testing of solid, this diffraction patterns, these are usually at the edges of the sharp reflectors or discontinuities such as cracks. Now these cracks are responsible for this. So usually the tip of a crack behaves as point source, spreading waves in all directions due to the diffraction of the incident wave. Now this is the importance of the crack, how it is acting as a point source. Okay, now piezoelectric transistors. So this is also an important topic for this in ultrasonic testing. So you can say that the conversion of electric pulses to mechanical vibrations and the conversion of returned mechanical vibrations back into the electrical energy. This is for ultrasonic testing. Okay, that we studied from the starting. From the starting, we are studying that this is the basis of UST, ultrasonic testing. Now, this conversion is done by the transducers by using a piece of piezoelectric material, like a polarized material having some parts of the molecule positively charged while the other parts of molecule are negatively charged. Electrodes attached to the two of its opposites. So when an electric field is applied across the material, okay, there is an electric field. You can see the electrical source in the diagram. So when electric field is applied across the material, the polarized molecules will align themselves with the electric field, causing the material to change the dimension. You can see in the diagram also how it is done. So in addition, a permanently polarized material such as quartz or barium titanate will produce an electric field when the material changes dimensions as a result of an imposed mechanical force. This phenomenon is known as piezoelectric effect. Okay. Now, the active element of most acoustic transducers. Most acoustic transducers used today is a piezoelectric ceramic, which can be cut in like a piezoelectric ceramic, and this can be cut in various ways to produce different wavelengths. A large piezoelectric ceramic element can be seen. You can see this image of a session low frequency transducer. The most commonly employed ceramic for making this transducer is lead zirconate titanate. Is lead okay? The commonly employed ceramic for making transducers is lead zirconate titanate. The thickness of the active element of this of lead zirconate titanate, the thickness of this active element is determined by the desired frequency of the transducer. A thin wafer element vibrates with a wavelength that is twice its thickness. Therefore, piezoelectric crystals are cut to a thickness that is half the desired wavelength, half the desired radiated wavelength. Okay, piezoelectric crystals, these are cut to a thickness of that is half the desired. Okay. Now here this line is very important. The piezoelectric crystals are cut to a thickness that is half the desired radiated wavelength. Now comes the important thing. The higher the frequency of the transducer, the thinner the active element. Okay. If you increase the frequency of the transducer, the thinner the active element will be. Now, the characteristics of piezoelectric transducer. So, you can see that the function of the transducer is basically to convert the electrical signals from mechanical vibrations, transmit mode, and the mechanical vibrations into electrical signals in the receive mode. So, many factors such as material and mechanical and electrical construction and the external electrical and mechanical load conditions, these conditions like these influence the behavior of the transducer. Okay, now a cuts way of a typical contact transducer is shown. You can see in this figure. So to get as much energy out of the transducers as possible, an impedance matching layer is placed. Okay, you have a impedance matching layer that is placed between the active element and the phase of the transducer. I repeat, to get as much energy as out of the transducer as possible because it is responsible for that. An impedance matching layer is placed between the active element and the face of the transducer. Now, optimal impedance matching is achieved by sizing the matching layer so that its thickness is one-fourth of the desired wavelength. This keeps the waves that are reflected within the matching layer in phase when they exit the layer. So if you talk about contact transducers, the matching layer is made from a material that has an acoustically impedance between the active element and steel. If you talk about immersion transducers, so immersion transducers have a matching layer with acoustic impedance between the active element and water because it is immersed in a medium that is called maybe water. Okay, so contact transducers also incorporate a wear plate to protect the matching layer and the active element from scratching. Since it is in contact, so to protect it from scratching, they also incorporate a wear plate. The backing material supporting the crystal has a great influence on the damping characteristics of the transducer. You can see in the diagram how the backing is written. And there is an active element, there is a matching layer, and the waves in phase are shown with this. Okay, so using a backing material with an impedance similar to that of the active element will produce the most effective density. So such a transducer will have higher bandwidth resulting in higher sensitivity and higher resolution. Okay. Now as the mismatch in impedance between the active element and the backing material increase, the material penetration increases, but transducer sensitivity is reduced. So mismatch is should be avoided. Ah, so I think we should start with the MCQs now because MCQs are also important now. So let me search MCQs. Right. Now this dash equates the ratio of material velocities to the ratio of the sines of incident and refracted angles. What do we call this ratio? This is called as a Snail's law. Okay, we had discussed about this sine of theta 1 upon VL1 is equals to sine of theta 2 upon VL2. The Snail's law. Okay. When an ultrasonic wave passes through an interference, I repeat, when an ultrasonic wave it passes through an interference between two materials at an oblique angle, and the materials have different indices of refraction. So both reflected and the refracted wave are produced. So what do you think? It is true or false? I repeat, there is an ultrasonic wave. It is passing through an interference between two materials. There are two materials at an oblique angle. And the materials had different indices of refraction. So both reflected and refracted waves are produced. It is true. Now the dash describes the relationship between angles and the velocities of the waves. So what do we call this relationship? We call this as a Snail's law. Called as a Snail's law. Okay. The mode conversion occurs when a wave encounters an interference materials of different materials of different acoustic impedances and the incident angle is not normal to the interference. What do we call? We call is true or false? It is true. This okay. There is you can say different acoustic impedances. So in that case it is true. Therefore, investigating the dash of flaw allows the operator to build up okay, an image of the shape of the flaw. Okay, it can be mental and manual scanning and possibly visual if automated. So what do we call that investigation? Called as ecodynamics. Okay, we call it as ecodynamics. Now, this is an important question. Like in ultrasonic testing, the factor which is significant in ultrasonic testing, the factor which is significant in the response obtained from a defect. Now, try to understand the question and then you will get in depth meaning. In ultrasonic testing, the factor which is significant in the response obtained from a defect, which are the factors? Like the size and geometry, or the location with respect to adjacent surfaces, or the orientation of the major axis, or type of discontinuity and conditions of reflection. Type of discontinuity and the conditions of reflection. What do is possible? It can be a defect also. Type of defect or discontinuity and conditions of reflection, or all of these. I think all of these factors are significant in response to this obtained response obtained from a defect. So mode conversions occurs every time a wave encounters an interference at an angle. This mode conversion occurs for both portion of the wave that passes through the interference and the portion that reflects off the interference. I repeat and understand the question. Mode conversion, now talking about mode conversion. So mode conversion occurs every time a wave encounters an interference at an angle. This mode conversion occurs for both the portion of the wave that passes through the interface and the portion that reflects off the interface. It's called true. Now it can be seen that the waves interact near the face of the transducer. As a result, there are extensive fluctuations and the sound field is very uneven. So in ultrasonic testing, this is known as near field or Fresnel zone. Near field or Fresnel zone. Now in ultrasonic testing of solids, the diffraction patterns are usually generated at an edge at the edges of sharp reflectors or discontinuities such as cracks. So usually uh, such as cracks. So usually the tip of a crack behaves as a point source spreading waves in all directions due to diffraction of the incident wave. Okay, I repeat. In ultrasonic testing of solids, the diffraction patterns are usually generated at the edges of sharp reflectors or discontinuities such as cracks. Okay, usually the tip of the crack behaves as a point source, spreading waves in all directions due to the diffraction of the incident wave. This I told you with the help of diagram also. It is true. I told you that the diagram, you can see the explanation of this in the previous slides. So when a longitudinal wave moves from a slower to a faster material at an angle, and thus the wave is reflected, there is an incident angle. There is an incident angle that makes the angle of reflection of the longitudinal wave to become 90 degrees. This angle is known as, what do you call this angle? When a longitudinal wave moves from a slower to a faster material at an angle, and there is an instant angle that makes the angular reflection of the longitudinal wave to become 90 degrees. This angle is known as first critical angle. Okay, it's known as first critical angle. We have studied with the help of, I told you in the previous slides also. So this is all for today. You can refer these books if you want for increasing your knowledge in this topics that we discussed today. And if you refer these books, it will be helpful to you to increase your knowledge. So thank you all for today.